Okay, well, we're going to look at vectors and ultimately graphing vectors. If you know a little bit about vectors, you can skip this particular video and move on to the actual graphing example. If you don't have a background in vectors, then probably should watch this, and then it'll introduce graphing to some extent, and then you could move on to the graphing examples. So vectors basically are quantities that have direction and magnitude. And by magnitude, we mean um, if somebody says, what's the force on an object? Typically, you give them a number like 50 pounds. A lot of times in physics, they'll say, what's the magnitude of the force? And they mean the same thing. The magnitude is 50 pounds. The direction might be northeast. So magnitude is a word used to ask for the quantity of a substance. Temperature is a scalar, which means it only has a magnitude. And mass is a scalar. They only have magnitudes. They don't have directions. Temperature doesn't really have a direction. It just is. So that's the basics of a scalar versus a vector. And if you've done a little physics, then you know you've encountered displacement, which is a change in position, right there. You've encountered velocity, which can be in one dimension can be plus or minus. As we look in two dimensions, you can be north, south, east, or west. Acceleration in one dimension can also be plus or minus. You can have negative acceleration. It means you're going backwards or slowing down. And so these are directional quantities, and therefore they're vectors. They have direction is important to them. If you have a negative velocity, you're going backwards. And so that's important to know. Let's take velocity as an example. So we get an aircraft going 450 miles an hour northeast. In an ordinary coordinate system, you can't represent direction, but you can represent a value like 450. However, we make this a vector by drawing an arrow pointed northeast, and we scale the length of the arrow to represent 450 miles per hour. So maybe you say 1 inch equals 100 miles per hour. Then you know that 4.5 inches would equal 450 miles per hour. So you'd make a line 4.5 inches long. If that's an inconvenient scale, then you could make it 1 centimeter or 4.5 centimeters to represent those quantities. But you need a scale in order to draw this properly. The official, well, at least my definition of a vector, I don't know how official it is, it's a directed line segment, the length of which is proportional, as we just saw, to the quantity, the magnitude or the value of the parameter. For instance, the miles, 450 miles per hour. 4.5 inches would be the length that's proportional to the 450 miles an hour. And you must have an arrowhead on it. And that's often called the tip. There's the tip there. And the tail would be the back end of the arrow. And that's only for discussion purposes when we're saying how to add these things. So that's the basic definitions of a vector. Now, what's the point of the vectors? How do they work? So two people are pushing on this little block we see here with 30 pounds each. The total force acting on the object will be 60 pounds. If you said 60 pounds, give yourself a star. Okay, so that's pretty obvious. That's pretty straightforward. In fact, what would we do to show that with those arrows? For this simple case, we take the two arrows and we stack them tip to tail. And we see that 30 plus 30 gives us 60. If we drew them to scale, maybe 1 inch equals 10 pounds. Okay, then 3 inches would represent 30 pounds. So they could be two lines, two arrows, 3 inches long each. And that would give us a 6 inch long line, which would be 60 pounds. Okay. 3 inches equals 6 inches, which is now from our scale, which is equivalent to 60 pounds. So That makes sense. Now notice it would make no sense to stack the arrows like this. That makes no sense because, you're not, one guy isn't pushing in on the box and the other guy isn't pushing out. One guy isn't pushing left and one guy isn't pushing right. Likewise, it would make no sense to sketch the arrows like this. This is also wrong. This is tail to tail. This is tip to tip. Notice this would make one guy's not pulling left on the box and the other guy's not pulling right on the box. They're both pulling in the same direction. So when this is not tip to tip, tip to tail, and this is not tip to tail. This is what we would call tip to tail arrangement of the vectors. When you add them, that's how you would place them, tip to tail, right there. Okay, this is wrong, and this is wrong. That's tip to tip, this is tail to tail. So, and it would make no sense to do that. Now, well, that's pretty straightforward. Let's do a slightly more complex case. Suppose you're pushing at it at 0 degrees, and let me define direction here. 0 degrees is going to point that way. 180 is going to point towards your left. 90 is going to point straight up, and 270 is going to point straight down. This is a typical angular scale for mathematics and physics. It's counterclockwise is positive, oddly enough. Who came up with that? I don't know, but counterclockwise is positive. So we get 90, 180, 270 like that. So you're pointing there, you're pressing the box with 30 pounds at 0 degrees. But your friend pushes at it with a force of 30 pounds at some other angle in the first quadrant there. It looks like maybe 45, 50 degrees or something like that. How do we combine them? Clearly, you're not using the effort in the same direction. So it's not going to be 60 pounds towards your right. It's going to be something different. And because they're not pointing in the same direction, we have to combine the arrows in a different way. We add them in this way. Notice it would make no sense to have the arrows pointing like this because the guy isn't pushing the box backwards. Or to have the arrows pointing like this because you're not pulling on the box. Those two are wrong. We place them tip to tail, just like that. And we have the arrow pointed up at 45 or 50 degrees or whatever angle it is. I didn't specify it. It's not important right now. And so what do? Well, now we can combine those two arrows with a line. That line, you see that dashed line right there. That dashed line is the result. This is called the resultant old vector language of the combination of the vectors. We might call this the net force of the vectors, maybe a little more updated terminology. That's the net force. And notice it's pushing up and to your right. It's not pushing directly to your right. That's the combination. This is the essence of how you add vectors together. And in fact, let's compare that to our previous example. And what do we observe? Compare the length of the red arrow. I know it's at an angle, but compare the length of the red arrow to the length of the green combined arrows. And what do you notice? You should notice that even though it's up at an angle, that it's a little bit shorter than the green arrow, a little bit shorter. So you're not putting quite 60 pounds of effort in moving the box anymore. Some of that motion, some of that effort has gone into changing the object's direction. And so, how do we calculate that? That's what graphing is all about. And we'll see about that more in another video.